by Manny Almeida. We will be answering questions at the end, so feel free to submit your questions throughout the presentation using the Q&A feature. All right, Manny, I'm handing it over to you.
Okay, thanks, Shelley. Hello, everybody. Thank you for taking the time to attend this webinar. Webinar is going to be on basic ICP OES troubleshooting. Want to give people an idea, especially people with new systems or don't have a lot of experience with their ICP, just some basic information and how to go through some logical troubleshooting. Okay, so for the agenda, what we're going to look at is we'll look at some simple diagnostic tests, and these are designed to allow you to isolate which portion of the instrument is giving you the problem. Okay. After that, then we'll look at some common issues, common problems, the kinds of things that every operator runs up against at some point or another. And then finally, we'll just look at some very simple preventative maintenance. I mean, and the reason for the preventative maintenance is to prevent you from having to do the troubleshooting in the first place. So there's some generally simple things you can do to reduce the likelihood that you're going to have a problem with your ICP. Just before you dive into doing any troubleshooting, you should take a moment and review the manuals that you have. I mean, we're all the same. We only look at the manuals when we have a problem. But it's really helpful to have an understanding of what the system's doing. You want to understand how to operate and optimize and set up your sample introduction system. Look at the facts that are in front of you and use valid reasoning. Certain things that go wrong can't be caused by a nebulizer that's not running well. There are just certain types of things that they just don't follow. So you want to use valid reasoning so you're not wasting time. You want to really want to identify the root cause of the problem, so you can get to the bottom of it and solve it, and not just provide a Band-Aid. So, for example, if you're having poor precision, well, if you just increase the integration time to 60 seconds, that problem goes away. Well, you haven't really solved the problem. You just put a Band-Aid on it. Avoid a shotgun approach. I mean, you want to be methodical. You don't want to change everything at one time. You want to make incremental changes, change one thing at a time. And finally, be patient. Some problems, and we'll see that in the common problem section, are pretty easy to figure out by just a little bit of inspection. You look at something and you can tell it's not quite right. Some of them take a little bit longer. Some problems are subtle, particularly if they're intermittent problems. They don't happen all the time. And some of the diagnostic tests will be able to shed light on some of those intermittent problems that you may run across. Okay. The troubleshooting that we're going to go through are sort of designed for the Teledyne Leeman lab systems that we have, the Prodigy 7, which is the new instrument that we have introduced last year, and also the Prodigy, which is a system we still supply that's been out for a number of years. I've tried to make it as generic as possible so that a lot of it will apply to any system. There may be a few things or one or two things that are specific to these instruments as opposed to some of the other systems that are available. But we'll see. Okay. So the first thing you really want to do is you want to isolate where the problem is. And so the portions of the system that we'll look at will be sample introduction. And anyone, if you have experience with ICP, you know the vast majority of problems you have are going to come from the sample introduction system. It's just a fact. You also have the optics of the spectrometer portion of the system, and also the RF and the power supply. We're not going to look at any electronics issues. That's far more advanced than basic. You need schematics, meters, and generally that's when you're in the electronics. If you have electronics problems, that's really the purview of service engineers. Okay. So the first step for troubleshooting, it really helps when you have your instrument, is to keep a record of the instrument's conditions when it's running well. So most instruments will have a diagnostics page or something in the software where things like mirror positions are stored, where intensities are stored. For example, when you position your plasma or you align the plasma view, you use an element. Typically, we suggest people use manganese. Well, you can see what the intensity was. You can see the positions of the mirrors. And this will allow you to establish a baseline so that you can see, well, how much, if we're in a position where we're losing intensity, we can see how much intensity we've lost. Or if the mirrors, we can't pick up any signal from the plasma, we can go and see where the mirrors are now, where were they in the past, and go back to that position. So it helps a lot of, it can shorten your troubleshooting if you have sort of a baseline for the instrument. So on all my systems in the lab, I take a screen capture of the diagnostics page, and I keep a record of what the intensity was of my, when I position my plasma, what the mercury lamp intensities are for when I align optics. And then I'll have an idea when something's not right. I can go back and look at that and see where I am. So finding the root cause. So we're going to look at 3 different diagnostic tests. The first is what we call the mercury lamp stability test, and that primarily tests the optics of the system. So anything in the optical tank, the shutter, things like that will be tested by the lamp, and that'll isolate from the sample introduction system into the RF and power supply. So it'll just test the optics. We'll have an RF stability test, which is also, people will also call that an Argon test, and that'll help us isolate problems from the power supply or in the RF system. And then finally, we have what we call the Analytical QC test, or in the past, we've always called it a daily QC test. And that primarily will test the sample introduction system. And we have a few different elements and wavelengths in there and that are in there for a specific reason, and I'll get into that. And that allows us to isolate or to take a look at the sample introduction system and to see what kind of issues we have going on there. So the first one that we'll look at is the mercury lamp stability test. Okay. And like I said, it tests the optical system, and it's going to eliminate the RF and the sample introduction system. And on our instruments, the lamp, it's a pen lamp that's in there. It's always on. There's no, it doesn't move. We had on our early systems, the mercury lamp was actually would move in and out of the optical path. Right now, what we do is we have what we call the source mirror, which selects the optimum position in the plasma in both the axial and radial views, can also change position and allow the light from the mercury lamp to get into the optical system. Okay. So the mercury lamp stability test on our systems, it's a test that we do in manufacturing, and it's a test we also do on installation. So the test will be resident, in the software, the method that we use. If you have a different system, you can create that. So the mercury lamp test will consist, on the Leeman systems anyway, will consist of these 4 wavelengths. When you do that, you have to make sure you select the view to be mercury lamp, because you're not measuring it from the plasma. So that when the instrument runs this test, it will move the mirror and get the mercury lamp intensity into the system. Make sure all the wavelengths are aligned. You want everything just right when you do this test, because you're using it to eliminate the optical system as a potential area of problem. We define a standard of 100, and that way any drift that we see will be read out in %. And we typically use, for the basic test, to just get a really quick and dirty idea how things are going, use a 10-second integration with 5 replicates, generate a calibration curve with 3 replicates. It's not necessary to use a blank, because the mercury lamp is always going to be on, so there's no blank necessary. And then we tend to run it 5 times, and so that'll give us a number of readings of 25 individual readings, which is enough to give us the information that we want. The passing criteria for that with these 25 readings is that the RSD of these 25 readings be less than 0.3% for all the wavelengths. And that's sort of that's the passing criteria for that test. On the right-hand side, you can see it's a test I did on one of my instruments in the lab, and it passed fairly easily. The instrument's a year or two old, so it's telling me that my optical system, shutter assembly, and all that stuff on the inside of what, the spectrometer or the optics box is probably okay. Now, it is possible that, when you have an intermittent problem, that this test is too short for that, so you can extend these tests, and we can run mercury lamp tests over a period of an hour or longer. Interpretation of longer tests can be a little trickier because other things can start happening, but it will allow you to try to isolate or to catch an intermittent problem, which are the worst. If the problem's intermittent, it's a lot harder to isolate it. But you do have that capability. We just extend that time. Okay. The second test is what we call the RF stability test, or also called an Argon test. And again, that method is resident on the Leeman Labs ICPs. So to do the Argon test, if you don't have it, we create a method and we put those two Argon lines, the 451 and the 404 line. Again, we make sure they're aligned, and they will on a dual view or axial system, they're in the axial view. On a radial system, you would put those in the radial view. To be able to run this test, you have to remove the spray chamber, nebulizer and spray chamber, and we plug the torch. Typically, I do that with parafilm or Teflon tape or something to plug it. You do that because we don't want any trace of water vapor in the system at all. If you have a wet spray chamber and you're trying to do an Argon test, it will most likely fail. So you want to have the spray chamber off the system, or if you don't do that, the spray chamber has to be perfectly dry, and that's one cause of failing Argon tests is the spray chamber is wet and you still have some water vapor in there. So take the spray chamber off, plug your torch, and then run the test. Again, we define the standard, define a standard at 100. And that way we can see the drift in percent. And this test we use 20-second integration times with 5 replicates, calibrate with 3, and the same as the mercury lamp test, we'll run 5 samples and we'll generate 25 individual readings. Okay. This is just sort of showing the test with the spray chamber removed. I have a bit of Teflon tape wrapped around the end of that torch, so the torch is plugged. You want to make sure you add some auxiliary flow because you have no nebulizer pressure, and the discharge of the plasma itself can sort of will be closer to the auxiliary. So we put a little bit of auxiliary flow on just to push the discharge away from the injector and the auxiliary tube inside. You don't want to melt your torch. And again, a wet spray chamber will cause you to fail this particular test. Like the mercury test, the acceptance is less than 0.3% RSD, and so a passing test on the 25 samples, and the passing test on the same instrument that we did the mercury test on, showing that my RF is in pretty good shape there. So I don't have a problem with this short-term test. Again, like the mercury test, if I'm dealing with something that's intermittent, then I can extend this test again for a longer period of time. I can use shorter integration times. This is a 20-second integration time. I can use shorter integration times. I can do the same on the mercury test. So there's a number of different ways you can apply the test depending on the situation. Anything that's intermittent, we want to go for longer test and maybe shorter integration time to try and catch that whatever the perturbation happening is. Okay. Then finally, probably the more common test that people would apply would be the analytical QC test, or what we used to call the daily QC test. If I am having a problem with an instrument either in my lab or if I'm visiting a user site, I don't jump, as soon as something's wrong, I don't jump in and do the mercury and RF tests right off the bat. I tend to do this analytical test first, and then go ahead and look at some of the common problem things that we'll look at in a bit before I go into the mercury and and RF tests or Argon tests. Okay. So the analytical QC test is really designed to test the performance of the sample introduction system, though it can help other problems too. And the reason it can do that is it uses a specific set of wavelengths and elements in it that are based on those elements' spectrochemical characteristics. And we'll sort of lay that out in a moment. And these are tests, all three of these tests are very similar to the tests that we use in manufacturing to QC an instrument before it's shipped, and also to validate performance, some aspects of performance during installation procedures of the systems. Okay. Now the basis for this analytical QC test is rooted in, if you have some experience with ICP, we understand that emission lines can be categorized as hard or soft lines. And just for the definition, a hard line is a atomic or ionic line that has an ionization potential of greater than 8 electron volts. And in this case, for the purposes of this test, the cadmium line and the zinc line are hard lines. Soft lines are atomic lines with less than 8 electron volts. So in this case, it's copper. And another soft line is an ionic line that has a low second ionization potential. In this case, that's barium. And the reason that these are put in there this way is if there are issues. So let's go ahead and look at what the tests are. If you look on the left-hand side of the screen, what we call the spectrochemical pairs are on the left-hand side. So the spectrochemical pairs for the soft lines there are copper and barium. The hard lines are zinc and cadmium. And by definition, manganese and iron are hard lines, but they're not as hard as the other two. So they will respond differently in the plasma when certain types of conditions change. Cadmium and zinc, they're hard lines, so they're very sensitive to RF power. If the RF power drifts or changes, it goes up or goes down, then those lines will change in intensity. Soft lines are not as affected by power. They'll change to a much smaller degree, and the manganese and the iron are sort of in between, and they won't change quite as much. But they're in there as pairs, so if the RF is changing, say it's increasing a little bit for whatever reason over the length of the test, we'll notice that the cadmium and the zinc should track together, and those are the kinds of things that you're going to look at when you run this QC test. You want to see what the trend, are there any trends? Are all the elements drifting together? Is it random? Is anything all over the place? So if we go ahead and look at just some artificial tests that I've done, we'll see how this holds up. So here's a test that I did. I created the method, calibrated it with the standards, and we'll see the standards and stuff that we use, and then ran it a few times, and then increased the nebulizer pressure a little bit, ran it, increased it, and increased it. If you look on the screen, you can see that the spectrochemical pairs go right with each other. So as we increase the nebulizer pressure, that's going to decrease the temperature of the plasma, similar to decreasing RF power. You can see the same situation on the right-hand side where I decrease the power. Well, which elements had the greatest effect? The hard lines, the cadmium and the zinc, they're with each other, going right down step by step with the greatest change. The iron and the manganese are sort of in between there, and the soft lines, the copper and the barium, have some effect, but nowhere near as great an effect. So these are the kinds of things that this test, that this type of a test can point out, where you run the test and see what the results look like, plot them out, or look at wavelength scans. That's another way to look at this, and we'll talk about that in a bit. Okay. So we create this test with the pairs in it, so the copper, the barium, iron, the manganese, and the zinc and the cadmium lines, and we use those are the specific lines we use. You can create your own test. You can use your own pairs. If there are certain elements that you're interested in, you can do that. Just be aware that it's nice to have a couple different elements, because then if they track together, that's giving you some information. Make sure they're all aligned, of course. Depending on whether the instrument's an axial or radial, we use different standard concentrations. If it's an axial system, the concentration for all the elements except barium is 1. Barium is a factor of 10 less. On a radial system, we'll use a 10 ppm with barium being 1. Again, it's not necessary. I typically don't use a blank when I do this, but the manufacturing tests and the installation tests will use a blank. The high standard and one standard that's 10 times. We'll use these two. That's 10 times lower. But for my purposes, I always just run one standard and use that, not worry about a blank. I'll position the plasma using manganese. That's normally what we recommend. For people that that's in aqueous mode, if you're not running aqueous, you're running organics, you run wear metals or fuels or something, we tend to position the plasma using the iron line. And all of these things will hold true in an organic matrix also, but we typically use the iron 259 line to align the plasma. We use a 30-second integration. It's a relatively long integration, and again 20 replicates, and then we'll let that system run. Okay. And the results for the test are shown here. We'd like everything to be less than about 0.6% RSD, and the barium to a line, a little bit noisy line, we like that one to be less than 1% RSD. So we look at results. This is on a different instrument than the other tests, but this is a pretty good test. Shows a nice quality control chart printout. There's no drift. Everything isn't going up or down. Everything is right on top of each other. No spikes or anything. So this is a pretty good test. You can see the results on the right-hand side of the screen. Everything is below the 0.6% RSD, and the barium is below 1. So this is pretty good. This is a good test. So 20-second integration is long. If I have some intermittent stuff or things going on with the neb, I can repeat this test and run it. Oops. Excuse me. Just to reiterate, so when you run this test, the things you're looking for: trends. Is everything going up? Everything going down? If the instrument is not warmed up, the sample introductions change in temperature, you'll see all these lines may all be going up together, or they all may be going down together. Anytime you see a trend, something's not in control. Temperature's changing, a position's changing, something's changing. We want to see if there is a drift. Are the spectrochemical pairs tracking each other? Is both the cadmium and zinc, are they doing the same thing? And the copper and barium, are they doing the same thing? Or is it random? Right? If the results of the test are random, then that always leads me to believe I go and I have a sample introduction issue, and I got to track that down. My nebulizer, I have a leak, something in the sample introduction system. This is the test done on the exact same instrument as the test previously that passed, except I have a 1-second integration, and that's about a reading of about 120 samples. So it's about a 2 minute. You can see there's a lot more fluctuation in there, the shorter term. So I could extend this out much longer, so I can try and capture something that's intermittent. I don't have a pass-fail criteria for this. I know that the RSDs are going to be higher with a much shorter integration time. But again, this can isolate something that's happening on a much shorter time scale than your typical analytical integration. All these simultaneous solid-state systems that people use now, you tend to use much longer integrations than you did when you had photomultiplier tube instruments, where those integration times may be 1 or 5 seconds, where typically people use much longer integration times, 10, 20, or 30 seconds. That can really cover up a lot of sins on a sample introduction system. A nebulizer that you wouldn't be able to use very, very well on a sequential system with the photomultiplier tube will actually work okay with the longer integration time. So it's possible to just reduce the amount of of the integration time to try and catch something that's going on for you. Okay. So I said you can use shorter integration times. You can use a longer test for intermittent problems. You can also add to this QC test a mercury line and another argon line, and that sort of adds the mercury test and the RF or the argon test to this particular test. Sort of interpretation can be a little trickier. You may have to ferret out some more information. So it's not, I don't really look at it as being sort of a basic test. It's a little bit more advanced, but you can do that. Just when you do that, you have to make sure that that mercury lamp or the mercury line is set up in the mercury lamp view, so it switches it to that, so that you can actually see the lamp. And the argon line will be treated just like like the other element, and we typically would put its concentration at 100 so we could see the percent in there. This test will also, by doing this, you're also moving the source mirror, and that actually adds one more wrinkle to the test, where sometimes if you have a dual view system and you see you have it's running, the precision's not as good and you have elements both of the axial and radial view, this will help you isolate to see, well, maybe the imprecision has nothing to do with sample introduction. It may actually have to do with the positioning of the mirror going back and forth. And this test, in addition to testing the RF and the optics, is also testing that mirror. So it's adding one more wrinkle to it. And sometimes the more things you're testing at one time, then the information, the data can be sort of confounded. Something's not right, but now you're testing a bunch of things at once. Okay? So you try and there are tests you can do specifically to test the mirrors that we're not going to, a little bit more on the advanced side. Okay. All right. So here's a couple of QC test results on some instruments, on my instrument in the lab. On the left-hand side, this is a pump issue, and you can see things are sort of jumping all over the place. It's a relatively short test, but everything's sort of tracking. A particular pump problem may not look like this, but I know this is a pump problem because I took a couple of lock washers and jammed them in there so that one of the rollers wasn't turning, and so we had one roller that was completely stuck. So it was causing some issues. If you have a roller that's dragging, sometimes this will show that up. Again, a shorter integration time tends to magnify or tends to illuminate that kind of a problem. Usually, if I think I have a roller problem, I just sort of stick my finger on the pump and see if I can feel the drag going by. I can do that a bit more quickly than running this test, but that works. So that's another way to approach it. The one on the right-hand side, the nebulizer issue. I know I have a bad nebulizer. If I take it out and look at the spray is sort of pointing. When I hold the argon, the gas inlet arm down, the spray is pointing to the left a little bit, and I can see huge drops being ejected. I don't have a nice fine spray, so I put that in, and that's what I got. So it's pretty random. It's just elements. Nothing's really tracking. Things are just all over the place. So it's a pretty bad neb in there. So those are the kinds of things that the QC tests can point out for you. All right. So finding the root cause, and again, most of the problems you have when you're running into something, it's going to be in that sample introduction system. And that, so we'll look at some things: peristaltic pump, tubing, the spray chamber, torch, nebulizer. And it's really important to understand how the system sets up. What's right, what's wrong, how far in does the neb go, things like that. And it really helps, if you've gotten some training or to really understand how that sample introduction system it operates. Okay. So we'll move on now. So we'll look at some common problems that people have, and probably everyone who's run an ICP has had some of these issues that we're just going to look at. And these are the things that if I'm having a problem or if somebody calls me on the phone, these are just some of the things I'm going to say. This is, have you looked at this? These are the kinds of things that you want to look at. Some of them are going to seem really painfully obvious, and there are just times where even myself, it's the solution to the problem was the last thing I looked at because I really, how could that possibly have happened? So I'm going to be just as obvious and try and cover as many potential things that you might run across. So these are probably the most common things when people call in for support that they have no sensitivity or low sensitivity, my precision's no good, instruments drifting all over the place, can't light the plasma, I got torches melting, and my check standards are failing. So everybody runs across one of these kinds of things. So what I want to do is just take some time and so when I run across something like this, so if I go into my lab and I have no sensitivity today, or like the other day we didn't come into work, we had a blizzard, I was certainly expecting that the power was going to go out, and I was going to come in, I'm going to have an instrument that's totally shut down. Well, that's sometimes when you bring the thing back up, that's when some of these funny things start to happen. So I fully expected that we'd have some issues, power didn't go out. But so if I came in and I had no sensitivity, these are the kinds of things I would do. First, before you do anything, make use of the wavelength scan feature that your instrument has. If you have a solid state system, you're taking wavelength scans every time you run something, and the instrument stores that. You also have the ability to do full frame images on these solid state systems, so you can see everything. The wavelength scans and full frame images, or whatever your particular system may call them, it's showing you exactly what the instrument's seeing. And I believe wavelength scans I put more credence in wavelength scans than numerical output from the instrument. This is exactly what the instrument is seeing. So if I have problems, probably one of the first things I do is I just look at the wavelength scans, and they can tell me a lot. Okay. So first, no sensitivity or no signal at all. Right? So when that happens to me, the first thing I do is I look at the spray chamber. Is any aerosol being generated? Right? So is the nebulizer aspirating? I check the pump tubing. Not necessarily is the pump tubing new or does it need to be replaced. If you don't seat the pump tubing clamp in the holder real well, the whole thing can get dragged up into the spray chamber and it just can't aspirate. So you look in there, you see there's no mist inside that spray chamber. You look at the pump tubing, maybe that's it. Maybe the nebulizer's clogged. I've also seen is the drain hooked up. If I don't hook up that drain, I've seen very little aerosol makes it up into the torch. It's all going down, exiting the drain, which is now a gravity drain into the bottom of your instrument. If you keep that going for a while, eventually you're going to see a puddle. But that hasn't happened very often, but it is. I have seen it not so much on these cyclonic spray chambers, but on some of the Scots that have a much bigger drain hookup on the end, tends to just drain out, and most of the aerosol, or a lot of the aerosol, goes out the drain rather than go up into the plasma. Okay. If I do have aerosol and that all looks good, the next thing I do is aerosol getting into the torch. So I always keep a bottle of 1,000 ppm yttrium next to the instrument, and if there's any question, am I getting stuff into the torch, I run the yttrium, and you'll see that that's the sort of the vertical one there with the red, the pink, blue, and red. Or on the axial, you can see that with the recombination zone clipped off by the air knife. That lets me know I'm getting solution into the torch. If I don't see this yttrium going through there, and I can see I have aerosol, either I have my torch is plugged, or maybe the nebulizer pressure isn't high enough to be able to get that in there. So that's a very quick test. If you don't have yttrium, you can use sodium, the sodium bullet. You can see that orange finger in there. If you don't have the sodium, you can always get some table salt, or you go and look at the discharge. Can you see the sample? Is there a sample channel? Turn the neb off, and you'll see the sample channel will go away if it's there. If you don't have a sample channel at all, then if something's blocking, you get a blockage in your torch, tips melted, or you get some buildup of salt or something in there. Okay. If that all works out so well, then I start worrying, think about, is my source mirror aligned correctly? So we use manganese both on the axial and the radial view systems. So I'll look at that. Or did I align it on a blank? That happens. You grab the wrong thing, and the instrument aligns it. Now the the mirror positions are not really pointed at the plasma, or at least pointed at an area in the plasma where you're going to get some intensity. So this is a time you can, it's really helpful if you have that screen capture of the diagnostic. You can see what it should have been, and you just easily go back there and enter those values in and get back to where you belong. Or on this particular dialog, if you have an instrument, there's a reset default, and that'll go back into whatever positions are entered into the instrument, the configuration file when you boot the instrument up. This gets a lot of people where it's the source mirror is just not pointed in the right direction. It's just off in Neverland because they changed, grab the blank, and I've done it myself. I'm in a hurry, I grab the blank, or when you move the auto sampler and you put it to the wrong solution that doesn't have the element of interest in it. So that's one. The other, no intensity of signal. Are the optics aligned? Again, if you come in and the instrument's been off for a while for whatever reason, and you turn it on, maybe the optics aren't aligned properly. If the optics are aligned, are the wavelengths aligned? Right? So that's something easy to do. Take a look. Again, I can tell that by just doing a quick wavelength scan. I can see there. Not only am I not going to get any signal there, I'm probably going to get a nice negative number because that peak is sort of on top of that background point, so I get a nice big negative number, and that tells me that I have a bad background point, or my peaks have all drifted off because the instrument is in the process of warming up, or something has changed. In that case, rather than wait for the instrument to come back up to operating temperature, I'll just turn the heaters off and align everything up and run right from that point if I don't want to wait the required amount of time, which can be an hour or so, to be able to get that system back up. But this is something else that can prevent you from getting any signal. No sensitivity of signal, especially below 190 nanometers. These instruments all have, we all call them different things, purged optical path or a POP tube. So if I don't have any signal below 190, I'm thinking, well, are my windows clean? So that's below 190. That window there can be pretty dirty, and long wavelengths or visible wavelengths will pass through with a pretty clouded window. But below 190, if you have anything on there, and you may not even see what's on there, particularly if you run things like organic solutions, you get that sort of brown buildup on there after a while. You want to clean that off because that will prevent you from getting light throughput. The windows are okay. I mean, purge gas, is it on? Right? Do I have leaks in the system? I check those O-rings there. If the O-rings old, are they cracked? Are they in place? Right? Do I have the right gas? Right? If you have an instrument that allows you to use either argon or nitrogen, it's happened where people have hooked up an air tank, and well, air is 80% nitrogen. That's close enough. Well, it really isn't. So check, make sure you get the right gas hooked up. That's not often, but it's something that you don't normally expect. If I have that issue, I mean, I can go and I can look at and take. This is a full frame image. On the left-hand side, you can see I have the purge off, and so if you look at the bottom portion of that, I have really no signal below that carbon 193 line. The cutoff is about 190. The thing is, there's nothing going on there. The purge is off, so I don't expect to see anything. I can tell on the right-hand side, I can tell my purge is on. I have those are the nitrogen lines at about 172 nanometers. You can see they're in two different optical orders there, but if I have a purge and my purge is established and everything is set, I should be able to see those lines. If I do this full frame image and I can't see those lines, it's telling me that there's something wrong with the purge, or my windows are completely fogged up and I can't get anything through there. So it's a very quick test. You don't need a method. Just do a full frame, take image, go down there, and you should see this is on a Prodigy 7. The way these lines lay out on a Prodigy are a little different, but here you can see these are the two lines in two different optical orders, and actually see a third optical order off to the side there. So you should, if you have established purge, you should be able to see these lines. Okay. having no sensitivity is actually probably relatively easy to diagnose. It really tells you, man, something is just wrong or broke. Low sensitivities can be a little, things are working, but they're not working really well. So for low sensitivity, I just suspect, how's the nebulizer? Is it running at the right flow or the right pressure? Again, I look at the yttrium and the sodium. If I'm running organics, I look at that green finger. You can see that sort of down on the bottom there. See where that is. I'd like that to be somewhere right in that location, right in there. How's the viewing position? Right element, right? Again, we use manganese, could be iron for organics, but if you've grabbed, for some reason you've decided somebody's peaked it on sodium, it may be in such a position that where sodium is got great sensitivity, but all the other elements are pretty low because it's now looking really high in the torch. And the viewing position is more critical on the radial. On axial, you're looking down through the sample channel, so you really you don't have viewing problems very often on a radial unless you've picked up an edge or something. On a radial system, the intensity versus position in the plasma is much different. So if you've got that and you're way off, you may notice really low intensities. Is the torch positioned in the coil right? Is it too high? Is it too low? Prodigy 7 doesn't really let you position the torch in too bad a position. Can't shove it up into the coil. It's sort of limited. Prodigy has a different sample intro, so sometimes the torch might be too far back, might be too close, and that can change the intensities that you see. Right? Low sensitivity, well, optics or wavelengths are misaligned. They may not be completely off. You may just be catching the edge like that. So when you look at the calibration curve from yesterday to today, it's a lot lower for all elements. And you go and you look at your optics have changed. The position of the mercury lamp is a little bit different. Temperatures change, so go ahead and you realign the mercury lamp, realign your wavelengths. Most likely, if they've all shifted together, it's just a question of realigning the mercury lamp. Just as a matter of course, I always align my mercury lamp every day. Usually tend not to need to do that, but I just don't want to have to go back and realign everything or rerun something because I didn't do the mercury alignment that takes well less than a minute to do. So that's just part of my standard operating procedure. I just go ahead and align that mercury lamp. Okay. Low sensitivity, you have the right standards in there. I mean, the 10 ppm, it's really one. I mean, I've gone and grabbed the 1,000 ppm standard when I really thought I was grabbing the 10,000, and everything is off by a factor of 10. So AUREA standard's really old. New standards. I keep a 10 ppm standard that around the instrument that I have. Probably it's a multi-element that we get from a vendor. It's got 20 some odd elements in it, and I don't use that for calibration, but I use that when, hey, my sensitivity's low. I just go ahead and run that into a method, see where I'm at. A lot of times I'll just go ahead and remake the standards anyway before I do. We all make mistakes. Dilution factor of 10 happens a lot, so don't discount the calibration standards. Okay. Purge optical path again. It's maybe just a little bit dirty. There may be some leaks. Again, the window is not completely occluded, but it just may need to be cleaned. So I tend to clean these with a little alcohol, methanol or ethanol, and then don't let them dry. Clean them up with like a chem wipe or something before they dry, and then put them back in. And make sure the purge is established. If you just turn the system on and you haven't waited long enough, then you're going to see, your intensities for wavelengths below 190 are just not going to be very good. And the shorter the wavelength. So if you're trying to use the aluminum line at 167 nanometers, that purge has got to be there, or your intensities are going to be pretty low. So we look, check the purge, see how that's going. Okay. Next is poor precision, sort of common problem. Right? Just sort of not in any particular order, but uptake time's too short. So that first reading is different than a lot of the other readings. With modern systems, if your uptake time is too short, it doesn't necessarily mean that that first reading is going to be low. It can actually be pretty high. The way these systems work, they do a quick pre-shot to know what's in there, and if it doesn't see anything, then it doesn't have to really worry about that element too much, or at least it doesn't think it does. And then the next thing you know, halfway through the integration time, the sample hits, and you get much higher intensities than you'd expect. So make sure your uptake time is set right. Poor precision is a lot of times can trace it to the neb. So if I'm getting that poor precision, I'll shut the system down and I'll take the nebulizer out and I'll look at the spray. Remember deionized water? We've all probably done that where we've had a little bit of nitric acid in there, but do it with deionized water and look at the spray. The spray should be nice and smooth, not a lot of pulsations. You don't want to see big drops in there. And that may be clogging a little bit. Usually, when that point, I may actually let the nebulizer run, and I'll adjust the tension on that peristaltic pump. I tend to not put a lot of back pressure on there. I like a nice smooth aerosol coming off. If you tighten it up a little bit, there might be a little bit of pulsation. The longer integration time will generally cover that for you, so you don't have to worry about it. But you really want to make sure, like in that nebulizer QC that's failed, the nebulizer that I had there was just a bad neb, and there's no saving it. The spray was just terrible. Okay. Look at a stuck or dragging roller, and I just put my finger on it and then just see if I can detect it being dragged a little bit slow. If the peristaltic pump, if that roller is jammed, then you have to be a little careful because it'll drag your finger right into the edge there, and it hurts a little bit. But you can have that, and you can prevent your rollers from dragging and sticking if you just make sure you don't wait for the peristaltic pump tubing to fail before you change it. Right? You don't want acid getting all of that. I mean, if you have seen some of the peristaltic pumps that we see sometimes when we go in the field that have just been really abused, and because people don't change the tubing, they just wait till it breaks and get acid all over the place. If you take care of these things, they'll last a long time. Another thing, source of precision, is poor drainage from the spray chamber. So sometimes we'll just you just look at the drain and you'll see as it's draining, for some reason the buildup of solution down by the drain sort of bounces a little bit. Well, that affects the back pressure, and that may affect your precision. So we go ahead and try and clean that spray chamber up a little bit so that it drains better. Or you just see general beating up in the spray chamber because the spray chamber is really, it's got got some coatings on it, or sometimes people switch back and forth between aqueous and organic and didn't really clean it out really well. That can cause precision problems because you're renebulizing some of that stuff that's in there. So that's one approach, is to clean that spray chamber. There are reagents available that you can run through a spray chamber to clean it up. Some people will use like a 1% HF solution through a spray chamber just for a short period of time, and that'll clean it up pretty good. There are some other reagents that are safer. It's something from RB25 from Fluka is a thing you can get. I think that's the right description of it. That stuff's really, I like that. I prefer that over the HF, of course. It works pretty well. Clean up that spray chamber. Okay. Next is drift, and we see drift. Probably the biggest cause of the drift is your sample intro is just not warmed up enough. You didn't wait long enough. I like to wait. I turn everything on. I wait about 15 minutes, let it go, and then from that usually warms thing up. But you will see if your sample introduction system is changing, temperature of the lab's changing, you may see some drift. Is the pump tubing broken in, right? Brand new piece of pump tubing will, excuse me, will take a little time to settle in. Is your nebulizer clogging? You can see that will manifest itself in, you'll see some drift. Your check standards are going to start failing, precision start getting worse. Okay. If the optics are changing temperature, and this is a pretty bad example of an optics drift. So in this one, I turned the instrument off completely. It came in, aligned the optics, and turned the optics, the heaters on, and then did this change after waiting about 5 or 10 minutes. And then you can see how it's just really drifted right across. That's a pretty bad example of that. What's more likely for optical drift is you'll see something like this. Again, I can see that if I go to my wavelength scans, and it's not a huge drift there, but it's enough that it will adversely affect your results. This is clear. This is clearly in the optical system. This is not something that the sample introduction system is going to cause. It has nothing to do with that. It has nothing to do with positioning in the plasma. It's just your optics, your temperature is changing. Another way this can happen is if you have your torch exhaust is too low and the instrument's starting to overheat. Not very common, but it's not impossible. I've seen that with the exhaust is either not on or way below what the recommended flow is. And in our system, it's about 100 cubic feet a minute. Okay. Drift. Next, plasma won't light. We all sort of suffer through that occasionally. So plasma won't light. And again, this is assuming you have no interlock. So if you have an interlock, you got to address that RF power, current, or whatever the interlock has to be. The water's not turned on. So this is assuming you don't have any interlocks. Sample introduction leaks, you have air getting in there. So you've got O-rings that are not running, that are hard, or you've run organic solvents and they're starting to crack, and you get a little bit, you get some air in there. Plasma's not going to light, or it may light very difficult, in a very difficult fashion, right? Gas lines reversed on systems where you can actually manually plug in the two. I've done it myself. I put the auxiliary into the coolant and the coolant in the auxiliary, and I try and light the plasma. Sometimes, though, it will light. If you have enough auxiliary, if you have enough gas going, the plasma will light that way, and we'll talk about that in a minute for torch melting. Right, so look at the gas lines, see if you reversed them. The igniter lead's not attached. I've done that, done some work, pull everything out, and then I forget to attach the igniter lead. I can hear it ticking. When the igniter turns on, you can hear it tick, but nothing happens. If you don't hear that, and there's a button to turn on the igniter by itself, if you don't hear that ticking, then maybe the igniter's bad. Right? Got an old torch or a damaged torch, right? Eventually you got to replace them, right? Or a defective torch. There are some times where the torch, coming from the the manufacturer or the supplier is just not right. And that's something, get that torch returned, call them up, get that thing replaced. But it does happen, not very frequent, but it is possible that you have a defective torch. And next is bad gas. And again, it's not a very common thing, but it tends to be like the last thing you think about. All of a sudden, things are going great. We changed gas tanks, liquid tanks, and the next thing you know, can't light the plasma, and it turns out that you got a bad tank of argon. It's not the first thing that I check, but it is something that once I've exhausted everything else, that's what I look at. Okay. Next is torch. A torch is melting. Okay. Again, this is assuming that you have no interlocks. Okay? Again, gas lines reversed. Right. That can melt the torch. Once it's on, then all of a sudden you've got it lights, and then you have the wrong gases going through, the wrong flow rates. Torch is too deep in the load coil, right? The plasma forms relative to the coil, not where the torch is. So if you have a system where you can push the torch all the way in so that the injector tube and that auxiliary tube, and that's this area right here in the plasma, or on the torch, that's actually in the discharge, it'll melt, right? The torch in the photo there, that one melted because the coolant line fell off while I didn't put it on tight enough. And I did have some auxiliary. There was enough auxiliary running to keep the plasma going, but not enough to overheat, to prevent the torch from overheating. So that melted. Right? The torch is not centered in the coil. Again, the plasma forms where the coil is, not where the torch is. So if you're too far to one side or the other, you may not be having enough. You don't have the coolant cooling one side of that torch, and the torch can melt. Right? coolant flow is not high enough for a particular application. So if you're running things with high levels of dissolved solids, or you're running things with fusions, organics, you may have to increase the coolant flow for that. Right? You don't want to use too much coolant flow. You're just sort of wasting gas. But you want to make sure you have enough that the torch is not going to overheat, or the torch is not going to melt. Not enough auxiliary flow, where the discharge, the plasma is really too close to the injector into the auxiliary tube. So a little bit of auxiliary flow will prevent that, will push that plasma away. It will prevent the torch from clogging up, or gets from high levels of dissolved solids depositing on that. So put a little auxiliary flow in there, and a lot of times that's the kind of stuff that will prevent you from melting. Okay. Okay. We get a lot of times where people say, "Hey, call up, my check standards are failing." All right. So immediately after calibration, right? So check standards can fail immediately, or they can fail after you've been running it for a while, right? So usually right after calibration, I always look at to make sure that my standards are okay, and that the check standards are what I expect them to be, that I haven't made a mistake there. Right? Sample induction system's not set up pretty well. I got through the calibration, but now things have drifted a little bit right off the bat. Let's take a look at that. Carryover from the high standard, I've seen that where the high standard is not washed out. We do a reading on the check standard, and I fail because I'm getting some contribution from that standard. Another way is poor calibrations are accepted, where the calibration curve just isn't very good, and the check standard is going to fail. And sometimes what we see is when you run the calibration, so you generate a calibration curve, and then what the software does will report a value as if the standard was run as a sample. So you have a 10 ppm standard, you run your calibration, and then it'll show you that the 10 ppm is actually reading 9.8 or something like that. So if I have a 10 ppm check standard and it's plus or minus 10%, so that would be anything from 9 to 11, that check standard reading back at 8.5 because I have not a particularly good calibration. That check standard is going to fail off the bat, and I've seen people struggle with that, where they don't understand that, and they keep running it over and over again, and it's never going to pass until you correct that particular issue, right? Or and the other one, the instrument's just not stable during calibration, right? You should be able to get through the first calibration check standard without much difficulty, and that usually means that something is not right. And typically for me, it's always been the poor calibrations are accepted, or the check standard just isn't the right check standard. Check those samples. During analysis, you get drift over, that'll cause it. The nebulizers clogging, sample carryover, and because the rinse is not long enough, particularly in high throughput applications where people are really flying through there. They want to run a lot of samples. You get a high sample just before your check standard, and you get some carryover, and that causes it to fail. Okay. Check standards are not stable, and I've had this happen where just chemically there's a problem, and it doesn't happen right away, but in a long run, it can happen. I had a situation where you put a couple of standards together, and I had amongst a whole bunch of elements lead and barium, and without thinking, I needed sulfur, so I added sulfur, and then as the run progressed, the barium and the lead precipitated out, and I started getting check standard failure. So look at standard compatibility, see what kind of elements that you have in there. Those poor and again, poor calibrations really, how well those check standards are going to do. You really want the best possible calibration. Your analysis isn't going to be any better than your calibrations are. Okay. All right. Preventative maintenance. All right. This is a pretty short section. Preventative maintenance. So if you do this preventative maintenance, it's going to reduce the likelihood you're going to have to do troubleshooting. So like on the instruments in the lab, you got air filters on there, clean them. Right. If you don't clean them, they start to clog. Things overheat, optics start drifting, electronics start drifting, things get too hot. Do that. Pop windows, clean. Those should just be something you do on a regular basis, especially if you keep track keep track of your intensities. Intensities start dropping off, clean those windows so you don't have to track it, right? Change the water in things, recirculators and chillers. We recommend you change the water in your recirculator every 1 or 2 months. That the water-cooled tube, you don't want to get any any conductivity in there. So just go ahead, change that water over, right? Sample introduction O-rings. They're what isolate that sample introduction system from the outside world. You don't want to have air leaking in there, right? Or actually have things start actually leaking fluids out. Simple things. Just change those O-rings. Change the pump tubing, right? Not necessarily because it's worn out, but just don't let it go so long that it just falls apart and you have acid getting into that peristaltic pump in there. Peristaltic pumps have come a long way. They're pretty resistant. Those rollers are tough. But if you just start putting 10% or nitric or hydrochloric acid in there, you're going to run into trouble. Okay. And this is probably if you don't do any of the other stuff, this is the one thing that I always do when I run my instrument. At the end of the day, I let that thing rinse or deionize water for 20 minutes to a half an hour all the time. If I'm not here, I just let it, extinguish after running the samples and put a 30-minute rinse on it, right? And that way I don't run into problems where my spray chamber is got crystals in it because it's dried from, over the weekend or whatever. I don't take my torches and spray chambers out and clean them on a routine basis. That's because I sort of clean them every day by running solution through them. I think that's something that it's really a good idea to do. You're not going to have your nebulizers not going to clog up on you, and you keep everything nice and clean. That's one thing that's really good to do. And generally, instrument software will allow you to let the instrument run. You run unattended, and at the end, the plasma will extinguish, go through a rinse cycle, and extinguish. Take advantage of that. And if you do this preventative maintenance, you'll have a lot less problems on your day-to-day stuff. Now, if you have instrument component failures, that's a different story. The things that you can affect on the sample introduction system, if you do that maintenance, that'll seriously reduce the number of problems that you wind up having. Okay. So the summary. So we have some diagnostic tests that you can do. So you want to isolate the problem's location, mercury test for the optics, the RF test for the power, QC test for sample introduction systems. Right? Looked at some common issues and common problems, right, that we all suffer through, and then preventative maintenance. That's I love auto check. Reduce the likelihood of problems that you have. If you do that preventative maintenance, then you will reduce the amount of time you're going to spend troubleshooting. So you get more samples run through the system, and you'll spend less time being frustrated and trying to tame the instrument in your lab. And that brings us to the end here. I guess we could have questions. And I see some questions have come through. So let me see here. Okay, the first, right, is that one? Okay, first question is, if you have a dual view system, how do you know the best view to pick? Also, how do you know the best wavelength to pick? Is there a way? How can I? Oops. Okay. Okay, so the question says, if you have a dual view system, how do you know the best view to pick? Also, how do you know the best wavelength to pick? And what criteria are you looking for? Okay, so if you have a dual view system, then so you have an axial and a radial view. Depending on the content, so